Another question that had appeared was a very crucial question. What is meant by the statement, critical angle of diamond is 24 degrees? That means, what is the significance of this particular statement? What is the importance of this particular statement? What happens when such and such angle is exceeded? So the same question framed in different ways. What is the physical significance of it? What is the importance of it? Why is it that critical angle is 24 degrees for diamond? So in this case, what is meant by the statement critical angle of diamond is 24? How is the critical angle of a material related to the refractive index? We mean by saying critical angle of diamond as 24 degrees means that when the angle of incidence exceeds the critical angle value of 24 degrees, the phenomena of total internal reflection takes place. The correlation between critical angle and refractive index is refractive index of diamond with respect to air is 1 upon sin C, where C is the critical angle. How about this one? Again, sounds to be a simple one. It's just a single line answer. But still, if a ray of light passes from one medium to another, when a ray of light travels from one medium to another without any change in direction, what can be said about the refractive indices of these medium? What can be said about the refractive indices of these medium? Obvious answer here is the refractive indices of both the mediums is going to be the same, because there is no deviation in the path. The ray of light would travel undeviated. As a result, the media should have the same refractive indices. Another question, why do stars twinkle? Again, we did discuss this when we were discussing refraction, real depth, apparent depth. Stars are luminous bodies. They emit light of their own. A person on earth is going to observe the star through a large distance. Now, when the rays of light that are coming from star appear to reach the earth, we see that they travel through different layers of atmosphere. These layers of atmosphere have different optical densities. As a result, there is a deviation of path of ray of light. This deviated rays of light are extended backwards to give a relative position of star. But since the distance of the star from the Earth's surface is pretty large, we see the effect of twinkling of stars. Let's consider another question that had appeared. Looking at the figure, ray PQ and ray PR are two rays that are emerging from a point object P as shown in the figure. They're asking you to give a special name to the angle of incidence, angle PQN. They're asking you to give you a special name for angle PQN. Second part, you are asked to copy the ray diagram and complete it to show the position of image of the object P when seen obliquely. Third part, you are asked to name the phenomena that occurs if the angle of incidence is increased further. So first part, naming to the angle of incidence. The angle of incidence is called as critical angle. Why is it called as critical angle? Because the corresponding angle of refraction in this case in the denser medium is 90 degrees. Second part, you're asked to find out what is the position of the object after suffering refraction. So the apparent image works out to be at point P1 when we are extending the refracted ray. So we get an apparent position because of refraction. You're asked to name the phenomena also when the angle exceeds the critical angle. Which is the phenomena? Yes, it is total internal reflection. Again, a question that has been repeated quite a number of times, frequently has been asked, and definitely because it's a very important law in refraction. State Snell's law of refraction. How do we define Snell's law of refraction? For a given pair of optical media, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant, and that constant is called as the refractive index of second media with respect to first. Mathematically, 1 mu 2 is equal to sine I upon sine R. Coming down to the most recent paper, that is 2008, the question they had asked was, a monochromatic beam of light, monochromatic in the sense monochroma, chroma is nothing but wavelength or color, single wavelength light beam of wavelength lambda passes from air to glass. So it's a single chroma light that is passing from air to glass, optically rarer medium to an optically denser medium. Write an expression to show the relation between speed of light in air to the speed of light in glass. Also, as the ray of light passes from air to glass, they are asking you to state how the wavelength of light changes. Does it increase, decrease, or remain the same? Well, as far as the first part is concerned, we have the numerical formula as refractive index of glass is equal to speed of light in air upon speed of light in glass. So it's a comparative study of speed of light in air to speed of light in glass. At the same time, when a ray of light passes from one medium to another, which parameter remains constant? Definitely the wavelength. So in this case, the second part of the answer is the wavelength neither decreases, neither increases, but is constant as it travels from glass to air. Second question was a diagram based question, wherein they are asking you to draw a label diagram to illustrate critical angle, phenomena of total internal reflection for a ray of light moving from one medium to another. And we know that TIR always occurs from a denser medium to a rarer medium. Write the formula to express the relationship between refractive index of a denser medium with respect to the rarer medium and its critical angle. See, the question is repeated again, but in a different format based on the figure. So since it is traveling from a denser medium to a rarer medium, we consider a glass trough which is filled with water. The ray of light is going to travel from denser medium to rarer medium. The first ray of light goes away from the normal. second ray of light, where the angle is equal to the critical angle, will scrape through the surface, giving the corresponding angle of refraction as 90. The third angle is exceeding the critical angle, the angle of incidence greater than critical angle. In this particular case, we see that TIR occurs. As a result, the ray gets reflected back into the same denser medium. As far as the mathematical correlation is concerned, we have refractive index of water with respect to air is 1 upon sin C, where C is the critical angle of water. As I said earlier also, this particular chapter does not have numericals, but still, in a way, we are trying to give you certain numericals that are based on this particular chapter, which could be asked in the finest of its possibilities. Say, for example, this one. The velocity of light in diamond is given as 1,21,000 kilometer per second. The velocity of light in diamond is given as 1,21,000 kilometers per second. You are asked to find out the refractive index of diamond. What is one standard quantity that we know? One standard quantity that we know is velocity of light in air is 3 into 10 to the power 8 meter per second. Why? Because it's an electromagnetic wave. An electromagnetic wave travels with the speed of 3 into 10 to the power 8 meter per second. A very simple example to solve. We have the relation. The refractive index of diamond with respect to air. Refractive index of diamond with respect to air is velocity of light in air upon velocity of light in diamond. Substituting the values, 3 into 10 to the power 8 divided by 121 into 10 to the power 6. Thereby, we get the refractive index of diamond here as 2.48. Again, refractive index is a unitless quantity. Let's consider this one. A postage stamp appears to be raised by 7 millimeter when placed under a rectangular glass slab. So I keep the postage stamp below the glass slab so that it apparently appears to be raised by 7 millimeter. The refractive index of the glass slab is given as 1.5. You're asked to find out the thickness of the glass block. An interesting example. I mean, we see it actually happening. But when it comes into numbers, how do we solve it? Let the thickness of the glass slab be x millimeter. So I assume the thickness of the glass slab as x millimeter. Apparent thickness, since it is apparently being raised through 7 millimeters, what is the apparent thickness? Apparent thickness is x minus 7. That is original depth minus the raised height. Refractive index is nothing but real depth upon apparent depth. Refractive index of glass with respect to air is real depth upon apparent depth. So if I substitute the value, I get 1.5 is equal to real depth x upon x minus 7. If I cross multiply and solve, it's a linear equation in x. and we have studied linear equations, very simple to solve it. So we get the value of x as 21 millimeter. That means the actual thickness of the glass slab was 21 millimeter. How about this one? Calculate the velocity of light in a glass block having refractive index as 1.5. Given the velocity of light in air standard, that is 3 into 10 to the power 8 meter per second. We have the relation velocity of light in a medium upon velocity of light in air is refractive index of medium upon the refractive index in air. So if I substitute the values, I get 3 into 10 to the power 8 divided by velocity in medium is equal to 1.5 divided by 1. So I get the velocity of light in the glass block as 2 into 10 to the power 8 meter per second. Talking about how to remember this entire chapter, because there are a few broad-based classifications for this particular chapter wherein you can just go through it and recap it. So we start with the definition of refraction of light. When a ray of light travels from a denser medium to a rarer medium, it goes away from the normal, rarer to denser, towards the normal. This phenomena of deviation is called as refraction. Lateral displacement, perpendicular shift between the original incident ray produced and the emergent ray after suffering refraction through an optical glass slab is called as lateral displacement. Factors on which lateral displacement depends: 1. Thickness of the slab, 2. Angle of incidence, 3. Optical density, 4. Wavelength. Then we came down to one of the major laws in the refraction of light, that is Snell's law. For a given pair of optical media, the ratio of sine of angle of incidence to sine of angle of refraction is a constant, and that constant is called as refractive index of second medium with respect to first. Mathematically, 1 mu 2 is equal to sine I upon sine R. This led to a very important concept of real depth and apparent depth. When we talked about real depth and apparent depth, we definitely knew that there is an apparent position that has been formed due to virtual producing the rays. This production of rays or this elongation of rays after suffering refraction is being taken up by the rays. This elongated rays give you a virtual image. When these elongated rays are giving you a virtual image, definitely you see that the real depth is being affected. We see that the objects are bent. We see that the objects are being raised. We see that the object is taking a relative position, thereby causing for refraction. So real depth, apparent depth is again prime important. Secondly, then we went on to your concept of critical angle and total internal reflection. To critical angle. Critical angle was defined as that angle of incidence in the denser medium for which the corresponding angle of refraction is 90 degrees. So when the angle of incidence exceeds critical angle, we see the phenomena of TIR occurring. Now this phenomena of TIR again has got large number of applications, wherein we saw the concept of mirage, we see optical fibers, we see that the lower meniscus of water appearing to be silvery, and so on and so forth. So definitely this also plays a vital role in our day-to-day life. So in short, refraction of light is an important concept that we can never ever forget.